So the title, we'll call it magnetic field due to currents. So last time we talked about if we are given a magnetic field, what is the force a charge experiences? But today we want to do the opposite. If a charge moves, then what is the magnetic field it creates? So that is the question we want to ask. There are 3-4 configurations of, first of all, I should say that in a general arbitrary configuration for currents, it is usually difficult to calculate the magnetic field. So typically how we can proceed for a discussion of this kind is that we go for the configurations of whose results are known. So the first is going to be an infinite or finite straight wire, right, carrying a current I. So all these, so that's the first configuration. And what do you mean by that is, so there is a straight line that carries a current I. So that's a current I, right? And in principle, this could be infinite, right? It could keep going onto the left, onto the top, and it could be coming from the bottom. And what we want to talk about is what is the magnetic field this creates at some arbitrary point, as I have shown here. So let's say this is our reference point. So this is let me just for describing the parameters that we will use, let's call this angle theta 1 and that's angle theta 2. Right. And we ask what is the magnetic field at the observation point P, let's say. So that's your observation point P, and the magnetic field is given by, tell it again.
Mu naught I by 2.
Good. Mu naught over, let me say mu naught over 4 pi is there, and then there is I current, and it depends on the distance. So let me call, so what do you guys use for the distance between point P and the wire?
Distance.
Distance d itself. So let's say distance d, right? Is that what you guys said? So that's the distance d. Or if you guys don't mind, let me use, this will help in later terminology. Let's keep this as rho. Okay, so this is rho, the Greek letter rho. Okay. And it also has to depend on the length of the wire. And instead of telling it is the length of this wire, we will say this is sine theta 1 plus sine theta 2. And just to avoid a confusion as to in what direction do you have to measure angle sine theta 1 and sine theta 2, let's put this as magnitude. That is just to avoid any confusion that might arise as to in what direction do you have to measure the angle sine theta 1. So that's your magnetic field for a finite current carrying wire. Okay, but there is a lot of simplification if this was infinite. Okay, so let for infinite wire, what happens to angle theta 1 and theta 2?
Sir, that rho is a distance, sir.
Yes.
Tell that again. I didn't understand the question.
Rho value. Rho.
Yes. So you're asking where is the rho value?
So what is rho is asking? Rho is the distance between the point and the wire.
Oh, what is the rho value? Yes. So let me mark that. So this. So the distance between the wire and the point of observation will be rho.
Distance.
Okay. So the closest distance between the wire and the observation point. Yeah, I should have drawn that on the diagram.
Yes.
Okay, clear?
Mm.
If you're in, if it is a plane, then you would say it is x square plus y square, square root of x square plus y square. But just the distance between the observation point and the wire, the shortest distance. Okay. Often this wire is infinite in length, and by infinite we shouldn't be worried that, oh, this is an abstract concept. Infinite means with respect to rho, it is very large. If it is 100 times larger, that's good enough. Okay. If you're measuring it 1 centimeter away, and if your length of the wire is 50 centimeters, that's good enough for infinity within 1% accuracy. Okay. So for an infinite wire, now try to tell me what is theta 1 and what is theta 2. Usually this is what involves an interpretation in a problem. You have to interpret what is given to you. So if I were to stretch this length of the wire to infinity, what happens to angle theta 2?
Theta 1 is 90, sir.
I'm asking what happens to theta 1 if this wire tip was supposed to go to infinity. So let me point that out. Let me explain that. So as I make this wire longer and longer, this blue line makes it longer and longer. This angle theta 1 will become larger and larger, right? Right? If I put this farther down, this angle will become further more. And in the extreme limit, what does theta 1 become?
Parallel. Become parallel or what?
Yeah, that will become parallel, but what will become to the angle theta 1?
Parallel means what? 180.
No, the angle theta 1 is being measured with respect to the red line that I have drawn.
90.
So the angle theta 1 will become pi by 2, correct?
90 degrees.
Yes, 90 degree exactly, right? Pi by 2, so 90 degrees. So theta 1 will become 90 degrees for an infinite wire, and theta 2 also will become 90 degrees. If it was a half infinite wire, one of them is 0 and one of them is 90. So let me give one more example just so that it's clear. Half infinite wire, so this is a definition now. So half infinite, right? Is so that will be theta 1 will be equal to 0 and theta 2 will be equal to 90 degrees. Clear?
Okay.
Okay. So we can say the magnetic field would be equal to mu naught. If it was an infinite wire, there is sine of theta 1 becomes 1, sine of theta 2 is 1. So this will become mu naught I over 2 pi rho. Right? So this is for infinite wire. And B will be equal to mu naught I over 4 pi rho if it was a semi-infinite wire. And in general, the formula is whatever I wrote on top. Okay. So that's the first case. Just to summarize whatever we are doing, so we need to put three popular cases and then we can do problems. Any questions on this configuration? How to understand the configuration? We have a wire.
So in our book, instead of pi, they will use r, sir. Smaller.
Oh, so instead of rho, you mean, right? So let me use r. Okay, so that's good. Yeah. Okay. So let me use rho or r, right?
Okay, sir.
So let me use r here. Good. That will help. Yeah. Okay. Good. Okay. We should also ask what is the direction of this magnetic field? What is the direction of this magnetic field?
Direction of magnetic field. We should do by right hand from both.
Tell it again.
No, sir. Magnetic field will get inside only, no, sir.
Yeah, into the page, correct? You mean into the page?
Yes.
Very good. That's correct. And what about the magnetic field on the left side?
Magnetic field on left side. Like a clockwise, sir.
Is it coming out or going in into the page?
No, sir.
So the idea is that it circles the wire. Magnetic field circles the wire.
Yes.
So it is going into the page on the right side and it is coming out of the page on the left side. Does that make sense?
Yes.
So for example, I'm going to draw this here. So this is the magnetic field. Correct? It is going into the page on the right side and coming out of the page on the left side.
Okay, sir.
Okay, does that help? Yep. So we should be able to find what is the direction of the magnetic field anywhere near a wire. And what you do is you hold the wire. So you hold the wire with the right hand, with the thumb in the direction of the current,
Yes.
and the fingers give you the direction of the magnetic field. Okay, so that we will have to use all the time. And that feature is given by putting, since left hand side is a vector, I should have right hand side also as a vector. So that is given as phi hat. That phi hat means the curl of the fingers.
Yes.
Okay? So that's a symbol that tells you that, oh, this is in the phi hat direction. Because left hand side is a vector, right hand side has to be a vector. That's the complete feature. Okay? So that's your magnetic field due to a straight wire. So that's one thing we need to know. The second point is the magnetic field due to an arc of wire, like a circular arc. So circular arc, like a wire shaped in the shape of a circular arc and at the center. We don't do it everywhere, it is only at the center of the arc.
Okay.
So again, we will only give the formula, we won't derive it.
Okay.
So the magnetic field is, so let us say this is a circle, maybe I can draw a circle.
Mu naught I by 2R, sir.
That's correct. That's exactly correct. But let me do a small change to this.
Okay.
I'm going to make this into an arc. Okay. So it's not a full circle. So that's the center. So this is not a full circle. This is angle theta. Good. And that's your current I in it. And this point is your observation point. So using your right hand rule, what can you say about the magnetic field at the observation point? Will it be going into the board or coming out of the board? Like use your right hand rule.
It will be going inside, sir.
It will be coming out, right? If you were to hold the wire with the right hand so that the thumb is pointing in the direction of the current, then the fingers on the left side is coming out of the board, out of the whiteboard, correct? So let me say Z hat is coming out of whiteboard. Okay, so that's just so that we have the directions with us. And the magnetic field is given by, again, mu naught over 4 pi. Okay. And then there is I over the radius of the circle. So let's call that radius R. So this is the radius R of the circle. And angle theta in radians. Theta is in radians, And the direction is coming out of the board, so that is a Z hat. Clear? So now again, this is a general formula. So let's say a full circle. You had a formula in mind. For a full circle, what is angle theta?
Mu naught by angle theta.
No, just the angle theta for a full circle would be?
NAPA sin theta. Angle theta.
Like for a full circle, it is 360 degrees, correct?
Yes, sir.
But we need it in radians.
So it's 360 divided by 180.
So it is 2 pi radians.
Yeah.
Right? So substitute that. So magnetic field due to a full circle would be mu naught over 4 pi. So let me revise that. So mu naught, so there is a theta becomes 2 pi. So this is mu naught I over 2R, right? That's what you were trying to say. Right? That's what you had in. So this is for a full circle. What will it be for a semicircle?
4R.
Exactly. So it will be half of that. Very good. So semicircle would be pi, so it will be 4R. So this is mu naught I over 4R times C hat. Okay. Very good. Let's do one more formula, and that's all we will need. Right, and that is, so this is the third configuration, and that's called a solenoid. So this is a cylindrical coil. Of infinite extent. Okay. So the idea is you have a coil. So this is a coil, and you keep going and you go this way, come here, go this way. Is that clear roughly? Right, this is a cylindrical coil, and the current is going, let us say, in this direction. Right. So it is going clockwise. So I is going so Z is in that direction. It's going clockwise when looked down from a large z height. Is that clear what I mean? Yeah. So if I were in the xy plane, just to clarify that, so this is x and that's y, the current is going this way. Okay, so this way. Okay, that will be clockwise, and counterclockwise will be if you're on the xy plane. Right, that's counterclockwise. Okay, good. And the magnetic field is very simple in this case, and this is one of the popular ways of generating the magnetic field. It is in the direction of z, that is along the axis of the solenoid. Right. It is equal to mu naught times current I, and that's it. And it depends on the density, how many number of turns it has.
So small.
Small n though, but not the total number of turns, because total number of the turns will be infinity. This is an infinite solenoid. So n is equal to total number of turns, n, capital N, divided by the length of the solenoid. So this is turns per unit length. Okay. And that is the case inside the solenoid. It is good to ask what is the mag, and outside the solenoid it is exactly 0. Okay. So no magnetic field outside. So a very nice configuration of current. So you take for example, you take a small cylindrical object and tie a current wire around it, and if you make it very close enough and pass a current through it, you generate a magnetic field inside that coil. That is a simple way of making an electromagnet. Okay. So that's your 3 configurations, and with that, let us actually do some problems that were sent on the WhatsApp page yesterday, correct?
Sir.
Do you guys have access to that?
Yes, sir.
Yeah. So let's start with the first.
7 minutes. The current is open.